Okay, so today's video is going to be about not today or how you're supposed to take it, about quantum mechanics, and let's talk about one and only the equation E equal hv, our famous equation, which can also be written as E equal hf, where either writing V or F doesn't matter because they both equal frequency. Okay, and h here is Planck's constant. Okay, so Planck's constant, or what we when we talk about E equal hv or hf, this is nothing but some kind of relationship between, or if I have to say it better, h here is showing the relationship between energy and frequency. Okay, h is also known as the smallest scale. By smallest scale mean there is no measurement below this. Okay, which could also be seen from example, delta x delta p is greater than h over 4 pi, which is also known as h bar over 2. Okay, so then Planck's constant, the value for Planck's constant is h equals 6.63, I think 63 times 10 to the power minus 34 joules dot s. If let's check if the unit of j dot the Planck's constant is really j dot s. Let's see. E equal h f. Here let me use v. Okay, because I want to be a quantum physicist, so yes, I'll use v. So let's make h the subject, and then more simplified, what is E? E is nothing but energy. Energy can be described as joules over V is frequency, hertz, equals to h. So then again, here since they already said joules, so we can say, we'll just now expand h. What is h or frequency? What is frequency? Frequency is see this. Yeah, this is what frequency is. Is it? No, it is c over v, right? Frequency is c over v. As v, yes, c over v. And then what we see here is, what is c? C is meter per second, or I can write it as meter per second. And then, or if it's at the top, it will be meter per second over meter. Guess what? Meter cancels, we get s. And this combines with joules, so that we get joules dot s. That's our, so that means this is correct. The unit is correct. As even if you will use kinetic energy or any other any energy, because energy has many forms, you will get the same J dot S. Okay, then wait, where is this? Okay, yeah, then even you say E equal h v can also be same written as photon, because photon is nothing but light, and light is, this is what light is actually, light. Okay, and how mostly it's used over here, if we have if we have a atom and it has a free electron which can increase and decrease in an energy level, when it releases energy, which is the photon, which we don't write as photon mostly, we just write as E is equal to hv, because it is giving out energy, and energy is nothing but photon. Okay, so, and energy, I'll just say energy gone, yeah, arrow up is representing gone, and when there's an energy coming in, okay, this will be absorbed by this electron, and it will come down and it will come over here. Okay, so this is also one where E equal hv is also formed. One more thing, the important thing in E equal hv is that this very thing is describing a single concept, a single, very single concept, that energy is discrete. Okay, that's the main thing. Before Max Planck, when he was going through energy or density of this energy density, what he mostly suffered was that him getting his equation wrong. Okay, here's this equation that which was to combine this, okay, which was to combine this with energy, but what he got for energy was kT, and this is a chaos. This full thing is a chaos. Okay, this with inserted with this chaos, it gives you infinite energy, and infinite energy, infinite, sorry, wait, let me write, infinite energy is not possible. Okay, not possible. So what he did is that he made his own law, which is now known as Planck's law. Which is known as Planck's law. And from there came the start of quantum mechanics. Quantum mechanics was the starting point of Planck saying energy is discrete, and when he delved into the world of atoms and space smaller than that, to subatomic and particles, and then he noticed, then what he found is that nothing, or after that, mm, after him discovering this, and something new started, a new field, quantum mechanics started, and this field, then many came, like Niels Bohr came, like with his model, Bohr's model. Then came Schrodinger. I'm not, I think, not going through. But I do remember Niels Bohr was with, has been in the time of Einstein. Him and Einstein were friends and enemies at the same time, because Niels Bohr is in favor of quantum mechanics, whereas Einstein did not believe in quantum mechanics, even though he contributed to quantum mechanics. His paper, EPR paper, was actually, even though his EPR paper was wrong, still it had many good things. Because of that paper, we got many discoveries. Okay, so it was Einstein, Podolsky, Rosen, paper, something like that. Yeah. Then Schrodinger and his famous. Then now I'm just talking about Schrodinger, quantum mechanics history. Then his famous Schrodinger, Schrodinger's cat or thought experiment, Schrodinger's thought experiment, and the famous equation which governs the world of quantum mechanics, the most used equation, Schrodinger's equation, without which quantum mechanics is incomplete. Then Heisenberg, his Heisenberg's uncertainty principle, Heisenberg, Heisenberg uncertainty principle. Even this, without this, quantum mechanics is incomplete. What is Heisenberg's uncertainty principle? Is that again? I think I wrote here. Which was it? Where is it? Oh yeah, this one. This is Heisenberg's uncertainty principle. Okay. That again. Let me just explain it in detail. That that let's suppose we have a particle, okay, and we know that it's moving in this direction. When it's moving in this direction, we don't know its position. In terms, that's me saying its position in labor words. If I'm to say in proper quantum mechanics or proper knowledge of quantum mechanics, I would say that as what quantum mechanics actually says is that you cannot measure both with such that the preciseness or the accuracy of the other quantity decreases. So I mean say that if this is increasing, this will for sure decrease in preciseness, that you will not be able to know how fast or where it's going when you know where it is in that space. Okay, that's weird, right? It's like a weird concept that you know where it is right now, but you don't know where it will go. But when you know where it is going, you don't know where it is at that time. So it's just a massacre. Quantum mechanics is just chaos. But then there's this code that if you don't get amazed or if you don't get confused by quantum mechanics, that means you don't understand quantum mechanics at all. So being amazed or being shocked or not understanding it properly means you understood it. That's how I think of quantum mechanics as. Okay, then the most famous equation, Schrodinger's equation, it's one of the longest equation, plus it's I think it's world's second longest equation or hardest equation. Minus d over dt psi equals h, was it h, h bar square, h square over 2m d over d square over dx square psi plus v of x and psi of x and t. This is the Schrodinger equation. I may be being rough on it, but this is the equation. And believe me, this equation itself has a lot of meanings. When we talk about Schrodinger equation itself, it has a whole different topic you have to study. It has psi, it has Planck's constant, it has complex number I. Here V is constant, V of x, which is potential energy, which is constant. We're not moving it. Psi of x in psi of xt is again coming here. You might have noticed, sorry, pardon. You might have noticed that psi of x and t, psi of x to respect to x and t is being multiplied with each uh, quantity. We call this operators. Actually, this whole thing can be written as h operator psi. So what we say is that this psi is actually acting on this operator. In quantum mechanics, everything is taken as operators. Operators, okay? So this is what it means. then what we say is that operators, or then we have eigenvalues and eigenfunctions. Eigenfunctions are just what which gives us the returned value, the same value returned, and eigenvalues are what you know. Then we can study about particle. I'm just giving an overview of some of the concepts in quantum mechanics now. Then we can study about a particle using uh, potential well. Potential well infinite. Okay, so suppose we have this box we have this well. This well is such that it has. I have made videos on it. I'll just give you a small view of what this actually does. This what this does is that we can use this to study how the electrons or particles behave. Okay, we'll not go to mathematics of it. We just talk about what it does. We can study the behavior. We can study the energy levels. We can study the uh, the values we get, the eigenvalues we get. Okay, because what we get there too are when we try to work out how the particle will behave in this, we get is this uh, pi n over, no, not pi n over k, square root of a over x sine pi n over a, or it will be opposite, and pi over a, yeah, it will be, yeah, equal 0. This is first equation which tells about the vector or the value, and this is about eigenenergy, which is E of n equal E, and n is the whole number. Remember, n is a whole number. Always represents a whole number. So it will be En 8. Was it 8? No, not 8. H bar 2me over 2me over h bar equals to k square. So k square is what was k square? K is n pi over a. Okay, this is what it was. So we inserted this equation, we get 2m k square over h bar square. So we get 2m pi square n square over h bar square a square. This is what we get. Okay, and so this tells about how the energy of at each energy level, what will the particle look like, because in this what we actually see is this: we have energy levels, and at every energy level, if this is 1, this is energy level this is energy level 1, energy level 2, energy level 3, and at every, what you will observe is the number of curves. It increases every time. Okay, so on. So at every energy level it will behave different. Okay, yeah, that's it. This was it. The overview. First we talked about the main thing was this. Then I just talked about quantum mechanics and some of its history. Thanks.